So what we're going to do now is we're going to look at sketching graphs of parent functions from derivatives. And in other words, we're going to be looking at sketching the antiderivative from the derivative. So let's first start out with just some reviews of some definitions. So a function f is called an antiderivative of f on an open interval I if f prime of x equals f of x for all x on the interval I. Now we get a second definition, which is just a little bit of an addition to the first one, which is if f is an antiderivative of f on an interval I, and so that's big F, right, is the antiderivative of little f on an interval I, then the most general antiderivative of little f on I is big F of x plus some arbitrary constant c, all right? And so basically this is the idea of we're going to reverse the process of taking the derivative, all right? And this is going to be the foundation for taking the integral. So for example, the antiderivative of f of x equals cosine x, that's little f of x equals cosine x, is f of x equals sine x. And that's because the derivative of sine x equals cosine x. Okay, so basically if we reverse the operation of taking the derivative, right, we'll go from cosine x back to sine x. So like everything that we've done thus far in the class, what we also want to know is what about its graphing correlate? What about the thing that it has to do with in terms of graphs or the graphs of functions, right? Some of that analysis. So let's take a look at that. So let's ask ourselves, what is it that we know about functions and their derivatives, okay, when it comes to graphing? Okay, so functions and the derivatives. And graphing. Well, we can first start with the fact that if, I'll call it big F, is increasing, then f prime is positive. Okay, so if you remember that, what that means is that we know that if the derivative is positive, that means that f is increasing. Okay, and so that actually is our correlate, what we know about the antiderivative. One, if little f is positive, then big F, right, our antiderivative, is increasing. And we have the alternative, which is if big F is decreasing, right, then f prime, right, which is our little f, is negative. And so we could say the other way around, if f is negative, then big F is decreasing. Great. Okay. So that's actually going to be really important. Now, we also have if big F of x has a maximum, then little f of x, okay, equals 0. Or we'll call it f prime of x equals 0. Okay? So conversely, now we have to be careful about this one because remember, we can actually have our maximum or minimum, by the way. We can actually have a critical number, right? So a critical number that in fact is not either a max or a min, all right? So, but we do know that if f of x is a max or a minimum, then f prime of x is going to end up equaling 0, all right? So we'll utilize this to our advantage. So how about this? If f prime of x, or excuse me, if little f of x, our derivative, equals 0, then big F, right, our antiderivative, is a critical number. And that is maybe a max or min, a relative extreme. Okay? 4. Now, these next set, when we think about or when we consider what we might know about the parent function from the derivative, is now looking at the second derivative. So if f double prime of x equals 0, then we have an inflection point. A change in concavity, right? Now, on the other hand, what does that mean for the derivative? Well, if we think about that, what that means for the derivative is if f double prime of x is equal to 0, that means f of x has a maximum or minimum, because f double prime, okay, is the derivative of f. So if, we'll say, since f double prime of x equals 0, or equals f prime of x, then when f double prime of x equals 0, f prime of x, okay, has a max or a min, right? A change in concavity, assuming that we actually, do have that change in concavity. It is possible, just like it is possible for us to have a critical number that in fact is not a max or min. The same thing could be true for the second derivative as well, with regard to the first derivative function. And then 5, if f double prime of x, okay, is positive, or how about this? If f of x is concave down, then f double prime of x is negative. And then if big F of x is concave up, then big F double prime of x is positive. Okay, so what we want to do now is we want to think about what's that corollary. Okay, if f of x is concave down, then f double prime of x is negative. So that's the second derivative. Again, so f double prime is the derivative of f prime. So if the derivative of a function is negative, that means the function is increasing. So if f double prime of x, okay, is negative, or actually, let's do it this way. If f of x is concave down, then f, right, which is our f prime of x, is decreasing. And if big F of x is concave up, then f, little f, is increasing. So this gives us some parameters that we can use in order to identify information about the parent function, okay, from the derivative, and then also information from the derivative about the parent function. So what we've got here is if f is positive, little f is positive, then big F is increasing, okay? And if f is negative, little f is negative, then big F is decreasing. So if f of x equals 0, then f is a critical number, okay? So we know that it may be a max or a min, so we can understand that that might be a max or a min, depending upon what we see. Since f double prime of x is equal to f prime of x, then when f double prime of x equals 0, f prime of x has a max or a min, okay? And then that means that that's an inflection point. So this is an inflection point for f, big F. And then if big F of x is concave down, then f is decreasing, okay? If big F of x is concave up, then f is increasing. So conversely, okay, we've got actually, these two are kind of switched a little bit. If f of x is concave down, then f double prime of x is negative, right? So basically, if we look at whether or not little f is decreasing, right, then we have big F is concave down. And if little f is increasing, then big F is concave up. All right, so we're going to utilize those parameters. Let's actually put it in action to see how it works. So let's consider f of x, which is the derivative of f prime of x, or excuse me, is the derivative of f of x. So f of x equals f prime of x. Now, what we want to do now is we want to start to map some of the features that we have on f of x onto big F of x. So from little f of x to big F. Okay? So if I notice here, the first thing that I'm going to look at is I'm going to look at from 1 to 1, 2, 3, 4, 5, 6, 1 to 6, all right? Little f of x, or the derivative here, is positive, right? So I'm going to just write in here, f prime of x, okay, is greater than or equal to 0, okay, from, and I'll look, this is going from 0 to 6. And then also it'll go also from 10, 11, 12. This will go from, this is 12 to 14. Okay? Then I'm going to notice that f prime of x is, this is actually strictly greater than 0, is less than 0 when I go from 6 to 12. Okay? So what that means for me is that means that big F is going to be increasing from 0 to 6 and 12 to 14. Okay, so big F is increasing from 0 to 6 and 12 to 14, and it'll be decreasing from 6 to 12. Okay, which is great. That's good information. The next piece that I want to notice is these values where I have f prime of x equals 0. So f prime of x is going to equal 0 at 0, okay, and also at 6 and at 12. And if you notice, okay, f prime goes from positive to negative. Okay, so if I look at this and I think about that derivative interval that we talked about before, okay, I have at 0, okay, then positive for the derivative, and then I have 6, and it goes negative, and then at 12, it goes positive. And so if I look at this, what that means for me is that means that what we have is we have a we go from increasing to decreasing. Okay, so that means that 6 is a relative maximum, okay, or a local maximum. And then we're going to go from decreasing to increasing at 12. So that means that 12 is a relative minimum. Okay, now, before I put those on, and I am going to put them on in just a second, I want to recognize that if you remember, this is actually, it's f of x plus c. Okay, so I don't actually know where this thing is going to start. Okay, so let's just say that I'm going to start here at 0, 0. All right, but that's completely arbitrary. I don't have to start at 0, 0. I can start anywhere on this graph. I can start down here at 0, negative 3. Okay, that would be option 2. As long as x starts at 0, because that's where this graph is starting. X equals 0. Okay, so I'll start at 0, 0, and then I'm going to increase until I hit 6. 1, 2, 3, 4, 5, 6. Okay, and I'm gonna quick sketch this thing. I'm just gonna pretend that it's right up to here. There's 6, and then 7, 8, 9, 10, 11, 12. Okay, and I don't know exactly how far this is going to go down, but let's just say it goes down. All right. And then we'll decrease. Okay, and then we'll start increasing again until we hit 14. Okay, so you see this is increasing, okay, from 0 to 6. Big F is increasing from 0 to 6, decreasing from 6 to 12, okay, and then increasing again from 12 to 14 with a relative maximum at 6 and a relative minimum at 12. And we got that all from the first derivative information, okay? Now, let's take a look here now and see that if we notice, okay, on the derivative graph, okay, that the derivative has a max at 3. So that means that I'm actually going to go from concave, right, it has a maximum of 3. So f prime of x has a max at 3 and a min at 9. Okay, so what those are going to equate to is those are inflection points. Because the maxes and minimums, those are critical numbers, okay, and that means that the second derivative is going to end up equaling 0. All right, so I'm going to put in some inflection points. Okay, all right, and so I'll first start with this one, and if we look here, we're going to go, our derivative is going to go from increasing to decreasing. Okay, and so that means that since it's going from increasing to decreasing, that means that we're going to go from concave up to concave down. So we might look at something like this, concave up, right, to concave down. And then once we hit 9, what we'll see is we go from, our derivative goes from decreasing, so here's our derivative going decreasing to increasing. And that means the change in concavity at 9 is to go from concave down to concave up. Okay, so we're going to imagine this here. There's that. And then now we're going to concave up. Okay, and since the graph continues to increase, we continue to have a concave up graph anyways. Okay, so what we see here is we see, okay, so this, all right, is a min or max. So that inflection point is a min or max on f prime. On the derivative, same here, that's a min or max on f prime. And how we make that determination, okay, is based upon whether or not, right, we're increasing or decreasing, right? So notice that we're increasing on the derivative, and that turns this one here to concave up. So up. Start decreasing, right? And now what we see is we're down. Concave down, okay? Concave down. Until we hit 9, right, when we start increasing again on the derivative, and so this makes it concave up. So those are the features that we use when we are attempting to understand the relationship between the graph of the derivative and its antiderivative. Okay, we have to start to get comfortable with the idea of reversing the motion that we took from taking the derivative, right? Okay, so we know things about the derivative, right? Now what we want to do is we want to take that knowledge about what we know about the derivative and pull it back and use it with the antiderivative. Okay? Let's take a look at this function, all right? It's a bit more complicated. So we want to take a look at some different features, all right? So from 0 to 9, right, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, okay? What we'll see is that the function is in fact increasing in some way or another, okay? So here is big F is increasing, and that's because little f is positive, okay? Then we have something like a plateau here, and this is because, right, f of x equals 0 along that line, so that means f is basically plateauing, right? It has no slope at that point. Then we'll have f is decreasing along this line. So f is decreasing from, I guess, 12 to 15, and then it goes back to another plateau. Okay? Now, before I draw anything, now that we're getting a little bit more sophisticated, I want to notice some things in terms of concavity. Okay? So what I want to notice here is, take a look. At this point right here, little f prime of x is got to equal 0 along that plateau. Okay? So that means f double prime of x, which equals f prime of x equals 0. So this is no concavity. Right? It would be an inflection point if it was just a point, but it's not. Okay? It's not just a point. Right? Instead, it's entirely a place where there's no concavity over an interval, and so it's not just an inflection point. It's actually kind of like a big plateau. Okay. Now, what we do get, right? Okay, right here, because the graph is increasing, or f is increasing, that's concave up. For f, here, because f is decreasing, this is going to make the graph is going to be concave down. So we do have inflection. It's just not an inflection point. Okay. Then again, right, we have f of x equals 0, so we have f is plateauing, right? And it's going to have no concavity there, no concavity. Then down here at, we'll call this, what is that, 13 and a half, okay? At 13 and a half, we're going to have an inflection point because that's a peak. And then again, we're going to have, at our plateau, we'll have no concavity. For the peak, for the inflection point, it's going to go from, this is decreasing, so that's going to be concave down. And over here, we've got increasing, okay? So this is going to end up being concave up, all right? So we've actually found a bunch of information about our big F of x. So let's use that. What I'm going to do is I'm going to actually plot in all these points where I have some changes in concavity, some differences. So I'm going to have 1, 2, 3. I'm going to start at 0. I'll go to 3. Okay. 3 is going to be concave up. Okay. And increasing. So it's increasing because the derivative is positive. And it's concave up because the derivative is increasing. So I'm going to make this, let's just make it like that. Okay, there we go. And then there's my inflection point. Now, I'm going to get from 3 to 6, okay, from 3 to 6, I'm going to get no concavity. That means that I've got some kind of linear function. It's still increasing. Notice it's above the line, so it's still increasing. But what that means is that we're just going to have a flat line. No concavity, no curvature to the line at all. Okay. Then what I'm going to notice is I'm going to notice that now once I hit 6, from 6 to 9, okay, from 6 to 9, f is decreasing, and so hence it's concave down. So we're now going to make it concave down. All right. There's the concave down piece. Until up. Let's make it a little bit further up. Okay. There we go. And then we'll go back to no concavity, and f is plateauing for another 3 spaces. Okay, and that's because f of x equals 0. Okay, so hence you're at a max or a min. Okay, and in addition to that, no concavity, so it's got to end up being flat. Now we're going to start to be concave down. Okay, until we hit this relative min right at 13 and a half. So let's say that's right about there, 13 and a half. Okay, 13 and a half. All right. And then now we're going to switch to concave down. Okay, but notice we're still decreasing because our derivative is below the line. So the derivative is below the line, so you're still going to be decreasing. Okay. There we go. Okay. And then we're going to plateau again. We don't know if this is a min or a max. We don't know what's going to happen after it. We just know in the next 3 spots, we're just going to plateau, right? No concavity, flat graph. Okay? And so that is how we kind of break down the graph of a derivative to get the graph of its parent function. Okay, so there's a lot to really think about. There's a lot to, kind of like consider. It's the kind of thing that is going to end up really kind of helping you out later on as we start to think about the derivative and as we start to think about the integral. Okay? All right. So this completes the lecture. Good luck.